Welcome back to this nanostructured materials course, where we are discussing the synthesis, properties, self assembly and applications. We have finished module 1, in which we had 2 lectures, and in module 2 we have 2 lectures earlier. Module 2 is on synthetic methodologies, and in that the first 2 lectures that we have concluded was based on the sol gel methodology. The sol gel methodology, we showed how you can make nanostructured materials of various porosities, starting from a colloidal sol or a polymeric sol, and then convert it into a gel and then into the nanostructured material. It can be made in a film or as a monolith or as a porous interconnected structure. Today is the third lecture in this module 2, and this lecture and the next lecture will be on another method of making nanostructured materials. This particular methodology is called the micro emulsion technique, and we would be discussing in detail what are micro emulsions, how we can stabilize them, how we can use them to make different kinds of nanomaterials, and also how we can control the size and shape of various nanostructures. So, what are micro emulsions? So, micro emulsions are thermodynamically stable, optically transparent, isotropic dispersions of aqueous and hydrocarbon liquids. Hydrocarbon means non-aqueous medium, and this dispersion of aqueous and hydrocarbon liquid is stabilized by a interfacial film of surfactant molecules. So, what we have introduced here is we have a mixture of an aqueous or a water based solution and a hydrocarbon liquid like an oil, which is a non-aqueous medium. Normally, the aqueous and the non-aqueous will not mix, but how to make them mix is through a film of surfactant molecules. Now, these surfactant molecules are normally having a hydrophilic head and a hydrophobic tail, like soap molecules which you use in your daily life. These surfactant molecules have this tendency that part of the molecule can be immersed in a water or aqueous system, and part of the molecule likes to be in the non-aqueous medium. So, when there is a film or a bilayer or 2 liquids having an interface like oil and water, then when you add these surfactant molecules, they would like to be at the interfacial region. So, these surfactant molecules which are at the interface of the aqueous and the non-aqueous medium can arrange themselves in various forms. So, one of the forms by which these surfactants aggregate is like a sphere, and when you form spheres which are monodispersed, then you can get microemulsion droplets, and these droplets can have either water or oil with diameters of around 100 or less than 100 nanometers. We can control that, and that depends on the nature of the surfactant and of course, the amount of water and solvent, etc. So, microemulsions are monodispersed spherical droplets of water in oil or oil in water. Of course, we can also have microemulsions with certain different type of organization of the surfactants. Now, microemulsions and macroemulsions are 2 different things. So, what is a microemulsion? A microemulsion, as we just mentioned, is a transparent solution and is thermodynamically stable. So, if you see on the left, this is a transparent system where you can see through this solution. So, this is a microemulsion, whereas the macroemulsion is opaque and you cannot see through that, right. And the other properties of a microemulsion is the size of the droplet, that means what is the size of the surfactant aggregates in which the water or oil is present, and that size is of the order of 10 to 100 nanometers, and it has high surface area. It has ultra low interfacial tension. IFT is the interfacial tension between the oil and the water phase, and this is of the order of 10 to the power minus 2 to 10 to the power minus 3 millinewtons per meter. And you can form water in oil, that means very small amount of water droplets surrounded by oil and having at the interface of water and oil surfactants, that is called a water in oil microemulsion. Or you can have oil in water microemulsion, where the content of oil is very less, and this is present within these spheres, and you can also have bicontinuous type of microemulsions. And normally microemulsion will form at a critical packing parameter of or CPP of 1. On the other hand, macroemulsions are kinetically stable, they are not thermodynamically stable. They form large droplets of 1 to 10 micron in size, and that is why their solutions are not transparent, they are opaque. They have low surface area of 15 meter square per gram, and normally they will form the oil and water interface will have a interfacial tension which is much higher, some 1000 times or 10,000 times higher than present in microemulsions, and that is of the order of 1 to 10 millinewtons per meter, whereas in microemulsions it is 10 to the power minus 2 to 10 to the power minus 3 millinewton per meter. And so, there is a large difference in the interfacial tension present at the interface in a microemulsion and a macroemulsion, and that is why macroemulsions, because of this large interfacial tension, are not thermodynamically stable and they are kinetically stable. Now, you can get both water in oil as well as oil in water type of macroemulsions, but it is difficult, you cannot get the bicontinuous type of systems which you can get in the microemulsions. Then the formation of macroemulsion occurs at a critical packing parameter when it is greater than or less than 1, not when it is equal to 1. So, the thermodynamics of the formation of microemulsions can be explained by writing the free energy terms. So, the delta G m is the free energy change for the formation of the microemulsion, and that is equal to the formation of free energy change due to the change or increase in total surface area. So, when the microemulsion is forming, you are having a change in the surface area, and this delta G 1 is a term which is which relates that the energy to the enhancement in the surface area. Delta G 2 is the free energy change due to the interaction between the droplets. So, as these droplets are forming, they are interacting, and that brings about a free energy change which is given by delta G 2, and delta G 3 is the free energy change due to adsorption of the surfactant at the oil water interface. So, these three free energy changes are additive, and then you have an increase in entropy because you are dispersing the oil as droplets. So, the increase in entropy is because you are disturbing the order of water, and this enhanced disorder leads to an increase in the entropy, and that will bring about a term which is minus T delta S, where delta S relates to the increase in entropy due to the formation of the droplets, which breaks the order and creates disorder in the water medium. Now, if you represent these things graphically, so the delta G for the formation of the microemulsion, if you see that this is greater than 0 for emulsions. So, emulsions are unstable, and hence you see that the delta G m is always positive, and it becomes increasingly positive as you come to small distances. Whereas, if for stable microemulsions, you will have a minimum in the delta G of the formation of microemulsion, and this will be the distance at which the minimum free energy occurs will give you the size of the microemulsions. So, delta G m star Z is less than 0 for the formation of the microemulsion in a particular range of R. Now, so whenever the microemulsions are forming spontaneously, it can only do that when the interfacial tension is very small, and that is what we mentioned earlier, that the interfacial tension is small of the order of 10 to the power minus 3 millinewton per meter. Around that order the microemulsions form. If the interfacial tension is large, then it will not lead to stable microemulsions. So, again to discuss or show you pictorially what is happening, you have this two liquids, one you can consider the aqueous phase and the other is the non-aqueous phase, and the two are immiscible like oil and water, and you will have an interface at the where the oil and water meet. Now, if you shake them giving mechanical energy, you can mix them, but that is only stable for a small time, that is kinetically stable if you give some mechanical energy, and that is typically a emulsion. It is unstable and it is not transparent. However, if you want to make a stable microemulsion which is transparent, you add surfactant, and surfactant basically are these kind of molecules which has a polar head group and a non-polar hydrocarbon tail. So, when you add these kind of molecules in this system, this polar head group will go into the aqueous layer and the non-polar hydrocarbon tail will go and sit in the oil layer. So, it will be lying at the interface, but when you increase the concentration of such molecules, then you can get some surfactant assemblies like that. So, within the solution you will get these small spheres which are basically this kind of surfactant assemblies where these molecules have come together in the form of a sphere, and you can see the polar head groups are pointing inwards and the hydrocarbon tails are pointing outwards. So, this is a particular spherical aggregate of surfactants where you have a hydrophilic head groups pointing inwards. So, this will like water or aqueous medium to be inside, because the head groups are hydrophilic, because they are polar head groups, and the chains outside are hydrophobic. So, the oil medium will stay outside. So, inside this solution now you will have many such spheres which you cannot see through your naked eye. So, this will be transparent, but if you look under or use some technique, you can find this organization of spheres, and the water, one of the mediums, say the B is water, will be present inside these spheres, and only the oil medium will be outside. So, such a spherical aggregate of surfactants in this microemulsion is typically called a reverse micelle. So, a reverse micelle is a microemulsion where you have the water and oil, the water content is much less than the oil content and the water is trapped within the spheres. So, then you get reverse micelles. If you have the other system, suppose these spheres had these tail groups inside and the polar head groups are outside, then water would be in the medium outside and oil would be inside. In that case, it is called a micelle, and when the water and oil is nearly same concentration, then you may get a bicontinuous phase. So, typically you get a microemulsion where you have got these surfactant aggregates and one of the liquids is trapped within the sphere and the other liquid stays outside the sphere, and it gives you a transparent solution. So, this is what is the basic structure of a micelle or a reverse micelle, which has got spherical aggregates of surfactants, and this particular geometry can help you control the synthesis of nanostructures by controlling the diameter of these nanostructures. So, microemulsion we can now define is a dispersion of water in oil or vice versa, that means oil in water, which is stabilized by addition of surfactant and co-surfactant. We have introduced the term surfactant before. A co-surfactant helps the surfactant reduce the interfacial tension between the water or the aqueous medium and the non-aqueous medium. So, both surfactant and co-surfactant are basically helping stabilize the immiscible system by lowering the interfacial tension. Co-surfactants normally are some long chain alcohols or amines, and we will discuss about them. So, to form a microemulsion, you can vary the surfactant, co-surfactant, the water content, the solvent or the oil phase or the non-aqueous medium, the temperature. All this will affect the size and morphology of the surfactant aggregate, and hence any synthesis of nanoparticle will be affected by the variation in the size and morphology. The stability of the microemulsions is basically due to the decrease in the interfacial tension, and the free energy is related, or the free energy of formation of the microemulsion is related to the oil water mixing entropy and the interfacial film curvature energy. These are two things which contribute to the free energy, and the interfacial curvature energy is related to the surfactant rigidity and film flexibility. So, the interface curls when droplets are formed, and hence there is an increase in the interfacial area, and that is related to the free energy term due to surface area. So, you can look at the picture that you have this kind of droplet where the surfactant molecule tends to adsorb, and in this case if this is the head group which is polar, then it will, the hydrophobic tail will be going into the oil droplet or the non-aqueous medium, and the polar head groups will be in the aqueous medium or wherever there is water. So, this is the normal structure of a reverse micelle or a water this is the structure of a micelle where oil is inside and water is outside. So, this is also called an oil in water microemulsion. Now, so in general micelle formation is an entropy driven process. As mentioned earlier, it creates, whenever you form these micelles or this order of aggregate of surfactant molecules, there is a disorder in the structure of the water due to the micelle formation, and the driving force is that the alkyl chains want to be away from the aqueous solution. So, it tries to eliminate the contact between the alkyl chains and water, and that leads to the formation of these micelles. So, that is the driving force. So, this we have discussed a little bit earlier. This is a surfactant molecule which has a polar head group and it has a non-polar hydrocarbon tail, and we can control the size of the polar head group. We can change the charge on the polar head group. You can have many types of charges, positive, negative, neutral. You can have many kinds of these hydrocarbon tails, very long tails. We can have 2 tails and we can have 3 tails. So, you can design many kinds of surfactant molecules. Now, what is the effect of these surfactant molecules? It affects the growth of the particle, since it provides an initiation site for the intermicellar exchange. It stabilizes through the self assembly of these surfactant molecules, and the size and charge of these polar head groups and tails affect the packing and growth of the nanoparticles, which will be synthesized within these spheres, which may be in micelles or reverse micelles. Now, there are varieties of surfactants. For example, you can have anionic surfactants. For example, is SDS in short, which is a sodium dodecyl sulphate, or you can have with the molecular formula given here, you can have something which is called sodium bis 2 ethyl hexyl sulfosuccinate, and that formula is given here, and its commercial name is AOT. It is a very common surfactant, and these, as you see, will have a negative head group. If you dissociate this sodium ion, there will be a negative charge on the head group of this molecule. So, both these are anionic surfactants because they will have a negative head group when this molecule is dissolved in water. So, AOT and SDS are both anionic surfactants. You can have zwitterionic surfactants like Sb316, which is hexadecyl sulfobutane, this is the formula, and you can have cationic surfactants like CTAB. This is the most popular, one of the most popular cationic surfactants, where you have this 16 carbon chain. So, it is cetyl trimethyl ammonium bromide. So, you can see that is a cetyl due to the 16 carbon chain, and you have a trimethyl group and you have a bromide. So, once you dissolve this in aqueous medium, the bromide ion will ionize and remaining one positive charge will be on this nitrogen. So, you will have a cationic surfactant. So, CTAB is a cationic surfactant. Similarly, you can have DDAB, where you have a 12 carbon chain, again a bromide. So, there will be a positive ion on the nitrogen when this molecule dissociates in water. So, you can have anionic, zwitterionic, that means both positive and negative charges in this system, positive on the nitrogen and negative on this side. And you can have non-ionic surfactants, but with a polar head group. So, for example, you have tergitol NP9, this is the commercial name very commonly used, and then Triton X100, this is another commercial name with this kind of molecule. And in these cases, as you see, there is a ether linkage here, and that gives the polarity, although there is no charge on the head group, but it is a polar molecule, and these are non-ionic surfactants. So, this is an example of anionic surfactants, and you can see these are the negative charge on the head group, and this is the hydrocarbon chain. You can have cationic surfactants, where you have this positive charge on the nitrogen and you have a hydrophobic tail. So, this is the hydrophilic or polar head group, and this is the hydrophobic chain. You can have non-ionic surfactants like this molecule where you have a head group which is non-ionic, but it has some affinity for water, and this is the hydrocarbon chain which has affinity for oil or non-aqueous medium. You can also have surfactants like this, which is you know, an alkyl glucoside and a glucose ester, as where so they make a together an alkyl glucoside and a glucose ester make this alkyl polyglycoside, which is acting like a surfactant because it has a hydrocarbon or a non aqueous loving tail, and you have a polar head group, though uncharged it has some polarity. So, there is a variety of surfactants which is available. You can also have biosurfactants, that means surfactants which are known in nature, and these are some complex molecules. This is called a sophorophlipid, this is a glycolipid, and there are several such molecules which are available in nature. So, surfactants like this are useful if you want to do anything in pharmaceutical industry or the food industry, where biodegradable molecules are more important, and so these kind of surfactants can be used for applications in those kind of industries. Now, you can have phospholipids like this, which are known very well known, where you have this hydrophobic tail and then you have a polar head group which is acting here. These are neutral surfactants, but and also they are biosurfactants. So, neutral biosurfactants. You can have interesting surfactants which you can design. For example, this is a surfactant molecule which does not behave like a surfactant as such, but when you have pass carbon dioxide through the solution, then it becomes ionic and then it behaves like a surfactant. That means, it can then aggregate if you put it in sufficient quantity in a solution containing water and oil, then it can give rise to spherical aggregates or different shapes of aggregates like micelles or reverse micelles, depending on the concentration of carbon dioxide. So, the carbon dioxide triggers this molecule which is not a surfactant here, but in the presence of carbon dioxide becomes a surfactant. So, such surfactants are called switchable surfactants. You can have redox active surfactant. For example, there is a surfactant which is like a monomer, that means it is not organized in any shape, they are all loose, the molecules are separate, but when it takes up an electron. So, when if you give some electrons from an electrode, it picks up electrons. If it does that, then it starts aggregating. So, it becomes like an empty micelle. So, the hydrocarbon chains are inside and the polar head groups are outside. So, inside of course, there is nothing right now. So, this is an empty micelle, but if there is some oil, suppose you at the next stage you introduce some oil, a non-aqueous solvent, then these micelles can take up those oil and then they will become filled micelles, and then if you remove an electron, this aggregate structure will be destroyed and this will open up and the solvent will go and stick there, whatever is there, and they will then again be monomers. So, from monomers to spherical geometry or the surfactant aggregates in the presence of electron takes up some oil and then gives out an electron to break up and leaves the oil, and again you can cycle these monomers. So, this monomer to surfactant aggregate through either reduction and then opening up of the micelle through oxidation, this kind of redox active surfactants are also known. So, this is an example where you have used electrochemical assembly and disassembly of surfactants. You can do the similar thing in molecules which contain say ferrocene. So, ferrocene is this iron with 2 cyclopentadienyl groups, and the other side is a chain with some trialkylamine, and this is a hydrophobic chain. Now, if you take out an electron, then you can change this ferrocene to ferrocenium ion. So, there is a positive charge because one electron has been removed, and if you add an electron to this, then you get back this ferrocene derivative. So, you can go back and forth by removing electrons or adding electrons, and these are again redox active amphiphilic molecule. Amphiphiles are basically again surfactants. Anything amphiphile means that it has a possibility of adhering to hydrophilic as well as hydrophobic moieties. So, any surfactant is an amphiphile. Now, there are certain terms which are used in microemulsions and surfactants and reverse micelles, etc. One is what is called the W naught parameter, which is related to the ratio of concentration of water is to surfactant. So, how much water is there with respect to surfactant? So, for example, you can have aggregates containing small amount of water, that is W naught equal to 15, and they tend to form reverse micelles, and whenever you have microemulsion with W naughts greater than 15, you can get lot of water. Basically what you are saying is, as you are increasing W naught, you are adding more water in the system. So, water is to surfactant ratio is given by W naught. Now, you have another term called the CMC, which is called the critical micellar concentration, and this is the minimum concentration of the surfactant at which the aggregation of surfactants to a micellar structure will take place, and that is called the CMC or critical micellar concentration. For different systems, the CMC is different. So, if you choose a micelle, if you choose a surfactant A with water and say a solvent like hexane, you will have some critical micellar concentration, CMC. Now, if you change the surfactant A to surfactant B, keeping water and the solvent same, you will have a different CMC. So, the CMC depends on the kind of surfactant you are using and the kind of solvent you are using, etc. At the CMC, when the surfactant aggregation takes place, there is a sudden change in the properties of the microemulsion or the system. Now, these changes in properties can be studied easily if you study the viscosity or the light scattering or conductance or surface tension. Many of these properties will change sharply at the critical micellar concentration. So, it is easy to determine what is the concentration of the surfactant at which the micelle forms. Now, there is another term which is used, which is called the Kraft temperature. This is the temperature at which the solubility equals the CMC, and that temperature is called the Kraft temperature. So, these are certain terms which are used regularly in the study of microemulsions and surfactants and nanoparticle synthesis of surfactant using surfactants and microemulsions, and one has to understand these terms because you have to change these parameters optimally to get the right kind of surfactant aggregates, which will help you control ultimately the size and shape of the nanoparticles which you want to synthesize within these surfactant aggregates. So, here we show you, if you have a surfactant like CTAB, which has this cationic which is a cationic surfactant and has a polar head group and polar head group of at this trialkylamine side, and there is a long hydrocarbon 16 carbon chain. which is the hydrophobic chain. Now, there are you can find out what is the typical hydrocarbon tail length, and it will have a typical head group area. So, this head group area and the tail length are very important in understanding what kind of aggregate these surfactants will make. So, as you change the surfactant from C tab to SDS, which is an anionic surfactant, to Triton X 100, which is a neutral surfactant. So, you go from cationic to anionic and to non-ionic surfactants. If you vary the dimensions, you see here the length of the tail is 20.5 angstrom, whereas in this case with this 12 carbon chain the length is smaller. Obviously, this is 12 carbons and this is 16 carbon chain. So, the length will be smaller. In this case it is 16.7, and in this Triton X 100 it is 11 angstrom. So, you can vary the length. Similarly, you can vary the area of this head group. So, here as you see the head group area is very small in the non-ionic surfactant, whereas in these cases the head group area in the cationic surfactant C tab is much larger. Now, these will affect the type of geometry and the critical micellar concentration at which the surfactant aggregates will form. So, if you start, what happens when you start adding surfactants to say water? You have water and you are adding a surfactant molecule. Initially the surfactant stays at the interface. So, you have water and say oil or some other medium which does not dissolve in the which is immiscible in water. So, then the surfactant molecules try to remain at the interface with the polar head groups on the side of the hydrophilic liquid, which is water, and the tails point towards the liquid which is hydrophobic. After a certain concentration, that means after you have added 4, 10, 20 certain number of molecules of surfactants, these surfactants tend to aggregate, and when they tend to aggregate, they take the water within their aggregate, because the head groups want to be immersed in the hydrophilic part of the system, and outside you have the oil remaining. So, this is typically how, as you vary the concentration, the surfactant molecules agglomerate in a particular manner and they solubilize the water inside, and this is a typical formation of a reverse micelle. So, what is the W naught value, what is the CMC, those things are important to design the typical surfactant aggregates that you want in a particular system. Now, you can get not only this kind of spherical aggregates of surfactant, like this is the reverse micelle or water in oil, because water will be inside and oil will be outside, because the polar head groups are inside. This is the micelle where you have the hydrocarbon or hydrophobic tails are inside and the polar head groups are outside. So, this is a micelle which will trap the oil medium, and this is a reverse micelle which will trap the aqueous medium. These are spherical aggregates of surfactants, but you can get also other type of structures, like this is a lamellar phase, where you have this polar head groups on one plane like this, and their tails are inside, and there is another layer of polar molecules whose tails are inside. So, there is a tail, these are hydrophobic tails which like each other and they arrange themselves in these lamellar phases. You can have cylindrical micelles where you have this hydrophobic tails pointing inside, and on the surface of the cylinder you have all the hydrophilic or polar molecules on the outside. Similarly, you can have vesicles like these, which is like one layer inside another layer, and the vesicles are known in our living systems also. In living bodies we have vesicles, and these are typical bicontinuous structures which we said can also be present in microemulsions. So, you can have different types of structures of these surfactant aggregates which are controlled by the concentration of surfactant, oil, water, and the type of these individual chemical entities. These are some other shapes which are different. Here you can see a cone shaped surfactant which results in a normal micelle, and if you have this kind of a surfactant where you see you have a polar head group and you have 3 or 4 different tails, and that forms what is called a cork shaped surfactant, which is again it is a reverse micelle. Here it is of course a micelle, and typically if you have 2 or 3 hydrophobic tails, then invariably they lead to reverse micellar organization, where you can have aqueous medium inside. In the micelles you can have the non-aqueous medium inside. You can have more complicated structures which are interconnected cylinders like this, or planar lamellar structures, or onion like structures. That means there is one reverse micelle here, and then there is another organization of surfactant molecules such that you have 2 polar head groups interacting with each other here. So, these are called onion like structures. So, a variety of surfactant aggregates are possible which self assemble themselves under certain conditions in colloidal solutions. Now, there are certain parameters which govern, which depend on the length of the hydrophobic chain and the area of the head group, etc., and there is a parameter which is called the surfactant packing parameter NS, which is related to the volume of the surfactant molecule divided by the area of the polar head group, which is multiplied by the length of the hydrophobic tail. And typically if you do proper calculations of these numbers, you will find that most of the time you will get spherical micelles if this NS value or the surfactant packing parameter is 1 by 3, or you will get cylindrical micelles when it is 1 by 2, you will get lamellar micelles when it is 1, and you may get reverse micelles when it is greater than 1. So, in this equation all these parameters of length of the hydrophobic tail, the area of the polar head group, the volume of the surfactant molecule all come into the picture, which ultimately can be put together as one parameter and which gives you a guide to what kind of shape you will finally end up with when you use different types of surfactant molecules which have different lengths and different area of the head group. So, typically when you want to synthesize nanostructured materials using these microemulsions, you can start with thinking that you want to make spherical particles, it is the simplest, and so you start with reverse micelles as nanoreactors. Why we call them as nanoreactors? Because this moiety where there is an aqueous medium here and you will be synthesizing the particles within this. So, this whole thing is like a reactor. The only thing is this diameter is in nano dimensions, it may be 5 nanometers, 10 nanometers, and so these kind of surfactant aggregates with aqueous solution inside can be treated as nanoreactors. So, this is the aqueous core where you can do your reactions to give rise to inorganic particles. Of course, if you want to use nanoreactors to synthesize organic particles, then you will have to use micelles and not reverse micelle. This because in a reverse micelle you can only do synthesis with metal ions which get into the aqueous medium, and for organic systems this part has to be a non aqueous medium, and so you have to use a micelle where the hydrophobic tails should be pointing inwards. Here the hydrophobic tails are pointing outwards and the polar head groups are pointing inside, and so inorganic solids or nanoparticles can be formed within this reverse micellar core. Now, using this you can get monodispersed water droplets, which leads to small particles because it inhibits the growth and aggregation of particles, and it is easy to control the size and shape of the particle because you can control the size and shape of the aqueous core. Now, when you have this kind of system of microemulsion, the understanding of the phase diagram is very important, because you have water, you have a non-aqueous medium and you have a surfactant. Now, this is called a ternary phase diagram, and within this ternary phase diagram some compositions will lead to say microemulsions, some composition will lead to micelle type of microemulsions, some which are called oil in water microemulsion, or in some other area typically where you have got less water. So, you are away from water, these regions you will get water in oil microemulsion. Of course, you can also get gels or in certain regions of the phase diagram. So, what this phase diagram tells you, what should be the composition of your microemulsion system in order to get reverse micelles or micelles, and to understand this phase diagram is very important because you have to choose your system properly. So, if you want to synthesize a material in a particular surfactant oil medium, you have to know its phase diagram, because you want to know what is the composition of the oil, water, surfactant which you need to choose. And so, these are typical some examples of water. Isooctane is the non-aqueous medium, C-tab is the surfactant. There are different types of phase diagrams you can generate, and some phase diagrams are known in the literature, some you have to find out whenever you want to work. So, this kind of a ternary phase diagram is very important to know. However, if you add a co-surfactant, then you have not only water, surfactant and oil, you also have a fourth component which is a co-surfactant, and so you will have to draw or understand a quaternary phase diagram, which is still more complex. So, you have to use phase diagrams, and to tune the phase behavior you can control the temperature, the co-surfactant and the salt, and then you can understand what is called the water emulsification phase behavior. So, you want to make discrete water droplets in oil, and there is one term which is called the water emulsification phase boundary. You can have these water droplets only when you are at within the boundary, otherwise this will fail and you will get separate droplets of oil and water. So, WEFB, if you know, you can do the controlled synthesis of nanoparticles. So, basically you need to know the phase diagram of the system, which will tell you where is this water emulsification failure boundary. Now, the water emulsification failure boundary WEFB is also dependent on salt concentration and ionic strength. So, if you keep the same surfactant oil and water, but if you change salt concentration or ionic strength, then you see you can move to different or lower amount of isooctane, or because this is isobutanol, this is being used as a co-surfactant. So, if you add more sodium chloride, which is a salt, if you add more salt, you move this side, which means you move to lower concentration of butanol. So, butanol is being used in this system as a co-surfactant. So, with less co-surfactant you can stabilize the microemulsion system by adding salt. The salt actually gives ions, and these ions compete with the head groups for hydration. which lowers the hydrophilicity of the surfactant, and the repulsive interactions of the head groups decrease, and that means that your interfacial tension is lower and you need less amount of co-surfactant to achieve the condition of interfacial tension to go to 0. Now, is ionic concentration the only parameter determining the water emulsion failure boundary? No, ionic concentration is one parameter, but in the if you change the ions, both say compare sodium ion and H plus ion, both have one positive charge. However, H plus ion gets more hydrated than Na plus ion. So, the effect of H plus ion is more than Na plus, and you can see the shift is more towards less butanol requirement for stabilization of the micelles or reverse micelles compared to sodium ion. And this is basically related to the hydration ability of H plus ion, which has more hydration ability compared to sodium ions. So, you can change this behavior of the WEFB or the water emulsification failure boundary to lower values of 1-butanol by adding salt. Now, typically when you want to synthesize nanomaterials, what you do is we make microemulsions of say a metal A. So, if you want to make a compound AB, nanoparticles of a compound AB, in one of the microemulsions, that means you take A ions, and in another microemulsion you take B ions. So, you first create microemulsions by having your aqueous solution which contains the A ions, your solvent which is the non-aqueous medium, and the surfactant, and then in this you have the B ions in aqueous medium and then solvent and the surfactant. So, you get transparent microemulsion 2 and transparent microemulsion 1, and you mix these two microemulsions and then they collide and coalesce, and during this collision and coalescence there is exchange of A ions from here to B ions from here, and then you get the compound AB, and the size of AB is controlled by the size of these droplets. However, the size of this AB is not exactly equal to the size of these droplets, but will be larger than the original size of these droplets, because two or more droplets are interacting to give these particles. So, this is how you can prepare nanoparticles by the reverse micellar route using surfactants or microemulsions. Now, the kinetics of these intermicellar exchange. So, this is the step where you are having the intermicellar exchange, and the kinetics of the intermicellar exchange rate compared to the overall or bulk reaction rate is very important in determining the mechanism. Now, if the exchange rate is very high compared to the bulk reaction rate, then the exchange does not have any particular role to play on the particle formation. However, if the exchange rate, the intermicellar exchange rate, if it is slow, then it becomes the rate determining step in particle formation, and then the mechanism depends on the intermicellar exchange, and where first we there is an encounter pair, that is two micellar units come together to form a pair and then a fused dimer. So, in this intermicellar exchange, when this is the rate determining step, this is slow compared to the bulk reaction rate, then a mechanism has been proposed in 1987, where it is said that the two interacting micelles come together to form an encounter pair, and then they fuse to form the fused dimer, and this is the slowest step. So, there is a fast pre-equilibrium step, which is the association of the two droplets to give an encounter pair, and then a slow step for the fused dimer to form, and the rate constant for this exchange is given by these equations. During intermicellar exchange, when the fused dimer is formed, the exchange rate is dependent a lot on the curvature here. If the curvature is very high, then this exchange is more difficult. So, the interdroplet exchange of the particles is inhibited by the inversion of the film curvature in the fused dimer, and this, how much this will curve inside, depends on the film flexibility, and that will affect the micellar exchange. So, after the particle nucleates, that is the nucleation stage, then there is a growth of the nanoparticles. Now, the growth of the nanoparticles typically follows what is called the Ostwald ripening rule. It is a thermodynamically driven spontaneous process where large particles grow, which are energetically favored at the expense of small particles. So, some small particles will form and then they will dissolve, and some large particles will form, and this will continue till the larger particles become larger and larger, and the distribution, that is the particle size distribution, will become much narrower. That means, you will have a large number of particles of one particular size, and then you will have very few numbers of sizes which are much smaller. Now, this is called the Ostwald ripening process. This is the thermodynamically driven process, and during Ostwald ripening, what happens, initially you have many of these particles which are forming, many nuclei which form, and then the smaller particles dissolve, becoming larger particles. The inner core particles dissolve first, because the surface energy is higher at the inner cores. So, the higher curvature gives higher surface energy and easy to be dissolved. So, the inner cores dissolve first and the outer cores are present, and this is a model, and this is what is seen in experiment. So, you see the inner cores, it is dark here, and then it becomes lighter, and so this is a process by which you are getting this Ostwald ripening to give rise to these particles. And so, thermodynamically, this is the process, the Ostwald ripening process, how the after nucleation the particle will grow. So, we will stop our lecture here, and we will continue the second lecture on microemulsions. In the next lecture, we will continue how the particles grow using Ostwald ripening, and we will consider other aspects of synthesis of nanostructures by microemulsions. Thank you very much.